So we have today, chapter 9, energy trace and barrier analysis. We will most likely get done with this one today and have some type of activity on Wednesday. And then you have your test on Friday. So if you've not been doing your review sheets, it will be very helpful for you. You can use them when you take your test. So get started on those review sheets. So that you have them available to you and so that you can study them a few times before it comes time to take the test on Friday. And like usual, the test will be available online. It will be about 50 questions and you'll have about 60 minutes to take it. So you don't have enough time to look them all up in that amount of time. But if you have those review sheets all done, study over them a little bit, you shouldn't have to look up that many of them. And you should have all the answers that you should need to be able to take that test. And it's available one day only, only on Friday for 24 hours. So make sure you log in sometime on Friday to take that test. All right, so energy trace and barrier analysis. Energy trace and barrier analysis, or ETBA, is one means of providing adequate analysis of accident cause. In order to better understand the ETBA, we must first define the occurrences that can result from the release of various types of energy. So this is going to be one type of analysis that you're going to do after a failure has occurred. You have an incident is an unwanted flow of energy resulting from inadequate barriers or having a failure without consequence. For example, exposed wiring that is discovered not to be properly grounded, but has not actually been touched. So this chapter, when it talks about incident, it's not the same thing as an accident. It's any event where you have the potential for there to be energy transfer, whether that transfer actually occurred or not. An accident, on the other hand, is an unwanted flow of energy or an environmental condition that results in adverse consequences. So the difference between incident and accident is that you definitely had consequences with the accident. Okay, so make sure you keep that in mind for your testing purposes. And then also just terminology in safety. Those two words are not interchangeable, although some people try to use them interchangeably. Okay, an incident is always going to be that type of situation where there was the possibility for injury, but an accident is when the adverse effects actually occur. Okay, hence an accident can occur because of, an accident can occur because of a lack of adequate barriers and or controls or an unwanted energy transfer associated with the incident. The accident is usually preceded by an initiating sequence of planning or operational errors that eventually result in a failure to adequately adjust to change in human factors and or environmental factors. So we failed to take into consideration those consequences. And so that failure results in accident, injury, property damage, something of that nature. The failure can lead to unsafe conditions and unsafe acts that arise out of the risk associated with the subject's activity. These unsafe conditions and unsafe acts in turn provoke the flow of unwanted energy. When the proper barriers are not in place or are not adequate to control this energy flow, the resulting unwanted consequence or accident will undoubtedly occur. You're going to have some type of an event. Okay. Example that I'm going to give you is where a man was electrocuted while attempting to steal copper wire, because when you are working on the power lines, there's an extreme amount of energy that is carried through those lines. And there are procedures in place, typically when you're working on those lines, to prevent a transfer of that energy. In this particular case, this man was not trained and so therefore was not following those procedures when he came into contact with the power lines. Now, I'm going to warn you before I go on to the next few slides, there's some pretty gruesome pictures here because they are from the actual incident. So if you cannot handle that, you are free to close your eyes or look away for a moment while we are on those pictures, and I'll let you know as soon as we are past them. You just missed the warning that we're about to see some gross stuff. So if you can't take it, look away or close your eyes. Don't puke on the floor. That's the only thing I ask. All right. All right, let me, turn off this light so we can see a little bit, okay? So the deputies found a ladder propped up against the pole and cutting tools scattered nearby. The man's body was found nearby after utility workers arrived to shut off the power line. The man has been identified, of course, by the point that they did this one. This was an incident back from 2008. And according to the judge, or not the judge, the sergeant that was in charge of this, the man's body was found around 1 a.m. Thursday near the down power line on Highway 76. So basically they get a call, the power line is down first. And then when they go to investigate, that's when they find stuff is all scattered around and they're like, something's not right here. They start looking around a little bit more and they find the man's body, okay? So obviously this picture is not at 1 o'clock in the morning when the incident occurred. But this picture is the following day when they're able to go out and take pictures of the area in which the incident happened, okay? So you can see that the man's body is up here at the top. That was the saw he was attempting to use without disconnecting the power from the power lines. All right, and then this is the cut power line. So he didn't even get all the way through the main power line. He started cutting through. And of course, once he got through the insulation, that first little bit of the power line, probably he made it this far because this was probably the return. And so then once he hit into the part that actually was carrying the power out, that's the point at which he was electrocuted, okay? That's what was left of him. And you could see from the first picture where he climbs up the ladder. He's over here working on it and it actually blows it. You can tell from the way his arms and his body are kind of bent back like that, that when he was electrocuted, it blew him back from that power line. They then have to go up and of course, at this point, they have the power lines completely shut down so that they are not risking the possibility of electrocution to the people who are recovering the body. But you guys see anything else wrong with this picture? Right, this is failure to follow safety procedures right here. Getting in this bucket, they should have used some type of a man lift that is created for this purpose, rather than the tool that they chose to use for it, okay? This is just another view of the same thing where they're trying to get the body down. What was left at the end. You see like his shirt and everything is like absolutely melted to him. He wasn't even wearing like the lower grade electrical gloves that you would need if you were working on like the electricity in your house. And he definitely did not take into consideration the amount of energy that was going to be transferred from those lines, which is a much, much higher rate of electricity than what you would find. All right, that's the end of the gruesome pictures. So, and you know why people steal copper wire, right? Yes, you can sell it. At the time when this happened, there were people that were breaking into like empty houses and stealing all of the power lines out of the houses and things like that, all of the electrical lines out of the houses, because you could get a pretty good sum of money for copper at that time. I don't know if it's still the same, but it made it worth like going in and tearing out all of the electrical lines and then peeling off all of the insulation. I can't even imagine how long that takes you to peel off all of that insulation to be able to take that copper wire in. But there were a lot of people doing that at the time, mostly for the purpose of then selling it and using the money to buy drugs. But there were also a lot of people stealing the inside parts of air conditioning systems and things like that. And that was even happening here in Grant, Oklahoma. There was one of the churches here in town, I know that they came in at some point in the middle of the night and stole all the insides from the air conditioning units, all the ones that were sitting outside of the building, just kind of tear the top off, take all the copper coils out of it, and then you have no air conditioning in your system. So I guess they learned that trying to take it from the power lines was not a great idea after one incident had occurred, and so started looking for lower voltage options. All right, so the ETBA concept has been designed as an investigation tool with which to focus specifically on 4 primary areas of concern: energy sources within a given system. And if you've ever been through lockout, tagout, you know that an energy system is not just going to be electricity. Anything that can cause energy, whether that be the gravity flow, spring-loaded energy, anything that could cause Energy or movement is gonna be something of concern, okay? The adequacy of any barriers or controls within that system, so what control measures are in place to prevent that energy from coming into contact with people or the environment, the human factors interface, and then the eventual targets of unwanted or uncontrolled energy flow. The target may be either people or objects. All right, so the step one in performing our ETBA is to identify the types of energy associated with the project, program, or equipment. And again, we need to look at all the potential energy sources. So that may be electric, hydraulic, pneumatic, spring-loaded, gravity. It can be a lot of different things, okay? But we need to, and there may be multiple sources as well. So don't just stop with you found the electricity and then so it's time to move on to the next step. You want to make sure that you're identifying all of the potential energy sources at step one. Types of energy can include mechanical, things like rotating gears and assemblies, electrical, potential energy that could be released such as spring-loaded devices. Kinetic energy, moving energy such as swinging armatures or moving crane hooks. Natural energy could be things like wind, temperature, radiation, ionizing, solar radiation. Non-ionizing would be things like lasers, cell towers, etc. And then radio frequency would be anything with the electromagnetic fields that may be involved. Step one continued. So we found all of our energy sources. We also want to look at biological things like pathogens or viruses have energy on the cellular level, and it is the energy contained within these pathogens or viruses that enable it to proliferate within a person's bloodstream. So even when you're looking for energy sources, think outside of the scope of what you would normally look at when you're talking about energy sources. It's really just about anything that could be resulting in injury or illness to the person. Okay. Also other options like we were saying, hydraulic, pneumatic, steam. And then once you've identified all of the potential energy sources, it's time to move to step two. Locate the exact source of that energy as it initially enters the system or process. From this point, the safety professional will literally trace, that's why it's called energy trace and barrier analysis. We're going to trace that electricity from its source and plot that energy's flow throughout the entire system. Sometimes this will look similar to like a blueprint or a little schematic that's going to show you where does the energy go once it enters that machine or operation, where does it go once it gets in there, okay? Step three, wherever it may be possible for the flow of energy to contact a targeted element, like people or objects, the safety professional chooses adequate barriers or controls to put in place. So we're going to look for all the potential places we could come into contact with the flow of energy and then look at what controls do we need. Do we need to have on-off switch, emergency stops? Are there different types of guards that maybe we need to put in place, blocks, barriers, whatever it might be to prevent that person or object from coming into contact with the energy source. Step four, the safety professional then uses the energy trace and barrier analysis to identify all locations within the system where barriers are required. Evaluate the adequacy of any existing barriers that are already in place and determine whether or not you need additional ones. Determine the risk associated with each unwanted flow of energy and assign it a RAC code to that condition. So is this something that is going to kill somebody? Is it going to cause a severe burn or laceration or whatever it may be? And how likely is it that that would occur? So just like within all of our other analyses that we've looked at, we're using that same risk assessment matrix that we talked about since week one in this class, okay? Recommended barriers where none exist. So look at the potential for those incidents. And is there anything there that is not currently got a barrier in place that would prevent contact with that energy source? If so, make a recommendation for how we correct that particular situation. Once completed, the energy trace and barrier analysis will facilitate any subsequent evaluation of risk level that may remain in the system after recommended barriers are installed or residual risk. Is there any last little bit of risk that is still there, which in most cases, there's still going to be some level, but we want to bring it down to a level where it's highly unlikely that this energy is ever going to make contact with people. Okay, as stated earlier, the energy trace barrier analysis has great utility in determining the specific breakdown in energy barriers during an accident or incident investigation. The energy trace barrier analysis is also quite useful in the analysis of new or existing systems to examine the adequacy of energy barriers currently in place. So we can't, most often we're looking at this kind of retrospectively after an incident has already occurred. But if you are involved in the design phase of any kind of new equipment and operations, it's also an excellent opportunity to be looking at where those barriers should be at to ensure that we're preventing this energy from making contact with people, okay? The following example will evaluate an existing oxygen supply system installed at a fictitious hospital. Okay, so the oxygen system at Memorial General provides a high purity oxygen supply for use by individual critical care patients in the rooms as well as during surgical procedures. The system consists of the following major components as indicated in figure 9.2. So we have a 3,000 PSI, that's how much pressure per square inch that you're going to be able to get from the air, okay? So 3,000 PSI gaseous oxygen supply tank located in a fenced-in protected area outside behind the hospital. Okay, a main distribution service panel located in the hospital equipment room, which functions to operate the source supply and drop the pressure from 3,000 PSI to 250 PSI because you don't want to like that level of pressure like blowing in your face. That would not be a useful amount of oxygen to be blowing into your face, but you need that amount of pressure to get it from the tank outside all the way in to where the patient's rooms are. So it's got to have an area where it's going to go through a pump that's going to lower that pressure before it goes on into the individual rooms, okay? Seam welded conduit tubing, 1 inch in diameter, is used throughout the system to transfer oxygen supply from the main distribution service panel to the various locations within the building. Several in-room service panels are part of this system. Each patient's room and other locations where needed are equipped with an in-room service panel. So you can flip on the flow of air or oxygen within the room, okay? The panel consists of an isolation valve, a regulatory handle valve to reduce the supply pressure from 250 PSI to a usable pressure of 20 to 30 PSI, and then a pressure indicator gauge, a pressure relief valve, a spring-loaded check valve, and a cap interface port for maintenance operations only. All right, so the energy trace and barrier analysis begins with the identification of the types of energy involved in this case. For the purpose of this example, only the 2 primary sources are examined here. Obviously, the very first concern is the presence of an extremely high pressure in the confined system. The gas in this example is oxygen, is highly combustible and thus presents a second energy source concern, which would be its ability to explode if it is ignited, okay? Onto the worksheet, like all the other different types of analysis, this worksheet looks very similar to the others. In the first, you've got a drawing number, and what this drawing number is referring to, let me go back to the picture that I showed you earlier. There will generally be drawings like this that are done by the engineers that shows you where the energy is flowing to and from throughout that system. So each one of these drawings is going to have a little box down here that gives you the information about what building or what operations or whatever this is, and they will have a specific drawing number so that if somebody needs to go back to that to be able to look at exactly what you were looking at in this analysis, you're going to put that drawing number on there. Okay, the energy amount and type. So this one was a high pressure gas. I would give a little bit more information there and say 3,000 PSI oxygen. Barriers or controls that are in place right now are isolation valves, a fenced off oxygen tank storage area, shatterproof gauges and safety related components, distance from personnel and isolation or insulation inside service panels. And then we've got the potential targets, which would be the personnel and property. On each one, it's going to be either just personnel where they could come into contact with that high pressure oxygen, or personnel and property if it could cause damage to something other than the people because of the amount of pressure, okay? We've assigned a rack code to each one. analysis of barrier effectiveness. So this one, we're talking about the isolation valves, barrier adequate to prevent exposure. And that's the same assessment that you have for the other two with the distance from personnel and insulation inside the service panels. Their analysis of this is that barrier is adequate to prevent exposure to high noise levels. And then the recommended action, ensure proper procedures are established and followed so that the barrier remains effective. Increase security around the hospital grounds. This is for where we have the fenced off area around the tank that is outside, because that's going to be an area where we have high potential for energy transfer. If somebody were to access that area and they don't know how to, you know, what's in there or how to control the amount of pressure. With the shatterproof gauges and safety related components, we want to ensure the system design per code, that we're not, just like with the video that we watched last week with the subsystem failure, if we're not making things to code, although it is intended to protect people, it may not do its job appropriately. Okay, and then we have the controlled risk assessment code. That's with ensuring these recommended actions are taken into account, how low that is going to decrease the amount of risk that is in the system. And then, of course, over here in this last column, they got any applicable standards that would apply to this. So ASME is a standard that is going to have to deal with the high pressure oxygen that they have in the facility. And then also OSHA 29 CFR 1910-134 is also going to have a standard that relates to using compressed air. All right, so the conditions that were identified, like with the other types of analyses, once you do that worksheet, you kind of gather the information. The next step is to write up the official report. The condition that was identified, the 3000 PSI source oxygen supply is transferred into the hospital equipment room via a 2-inch supply line. Potential targets are going to be personnel contact with high pressure gas during maintenance and or loading operations. So that tells us what personnel are affected, where on the worksheet we just put personnel, right? The risk assessment code, it was given a 1C. The result of this potential risk of hazard is considered catastrophic with an occasional opportunity for occurrence. So you can see it's explaining how bad would it be if it went off, and how likely is it that it's going to occur? So you want to make sure with all of these analysis that when you assign those RAC codes, you're giving us both reasons why the probability and why the severity that you've assigned it, okay? Barriers and controls. There's currently an isolation valve in the line on the exterior side that enables complete energy system shutoff prior to energy flow into the facility. So the controlled risk assessment is that with that control in place, barriers are considered adequate with a controlled risk assessment code of a 1E. So it brings it down to highly unlikely that it's going to happen, but it's still a 1 as far as if it did, it would still be catastrophic. Okay. And then they do the same thing for the other conditions that were identified on the worksheet. So I won't read through all of those. You have that example in your textbook, but that gives you all the different kind of spelling it out, how it would be done. You may want to look through these before you guys come back to class on Wednesday if you've not already read this chapter, because chances are you're going to get another example of this. You'd be filling out one of those worksheets and then writing up the summary like you did for the last type of analysis that we did. That is all of that. Do you guys have questions over this? This one seems pretty basic, right? This one's probably one of the easier forms of analysis that we do. The harder part is looking up the standards that apply to it, because a lot of times the standards that are going to apply are not just going to be OSHA standards. Sometimes there will be other standards like building codes, fire codes, electrical safety codes, those kind of things that you may have to find to help you out in filling out the forms and providing the explanation for the risk assessment that you've assigned to it, or why you're making the recommendations that you. All right. If you have no questions, you are done for today.